All right, so we're in section 10.3. We're going to talk about cross products. We in the last section and in first semester we talked about dot products. We found the dot product of two vectors. Cross product is another way. That was the only way so far we know to multiply vectors. The cross product is our second way that we're going to multiply vectors. Different procedure, and it tells us different things about the vectors. So if we have vector u that is in unit vector form, u1 I hat plus u2 j hat plus u3 k hat, and v is our vector v1 I hat plus v2 j hat plus v3 k hat. We say the cross product u cross v equals, and I'm going to write kind of a long thing that looks complicated, and then we'll talk about a really easy way that we find cross products of vectors. So our cross product comes out to be, or defined to be, u2 v3 minus u3 v2 I hat minus u1 v3 minus u3 v1 j hat plus u1 v2 minus u2 v1 k hat. So this is our cross product, this long kind of complicated looking thing. Well, we have a really nice way to calculate the cross product. What we do is we find the determinant of this 3 by 3 matrix. Yes?
So is that plus or minus the u1, u2?
Which one?
The part with k hat, the minus or plus?
This is a plus. So we find the determinant of that 3 by 3 matrix. These things turn out to be our determinant of our 3 by 3 matrix. It's not really a determinant. This just gives us a nice, convenient way to evaluate a cross product. So we have a nice connection between what we did with vectors and what we did with matrices. And this is one of the reasons that we had to find the determinant of 3 by 3 matrices by hand, is because we end up having to find cross products by using a determinant of a 3 by 3 matrix. So what I want to do is we'll do a couple of problems where we practice calculating a cross product. Then we'll talk about some rules that go along with the cross product, and those will come out of the calculations that we do. And then we'll talk about the geometry. What is the cross product telling us? What does it give us? What do we get from doing the cross product? Because we get a lot of useful stuff. All right, so questions on our definition here. One important thing to note: the cross product is a vector. The dot product gave us a scalar, just a number. The cross product gives us another vector. All right, so let's do some calculations. Let's calculate a couple of cross products. So we're going to do 3 different ones using the same vectors, though. So we're going to say that u equals a vector I hat plus 2 j hat minus k hat, and v equals 3i hat minus j hat plus 2k hat. And we want to find u cross v. So we're going to make this determinant ijk 1, 2, negative 1, and 3, negative 1, 2. So I'm going to write out this determinant, kind of write everything out explicitly on this first one. We don't have to write it out this way. I just want to write it out in a little more detail so we remember how to do this. So for when we find our determinant, if it helps, put your plus, minus, plus up there. We always alternate signs. So the j hat component, the second one we do, is always minus. So I'm going to do I hat times the determinant that I get when I cross that row and that column out. So I'm going to write out the determinant there. So when I cross this out and this out, I get the determinant 2, negative 1, negative 1, 2. So we cross out the row and the column, and we take the determinant of the 2 by 2 matrix that's left. Minus, with my minus sign there, j hat, and then we're going to cross out that row and that column and take the determinant of the 2 by 2 matrix that's up there, 1, negative 1, 3, 2, plus k hat times the determinant I get when I cross out that row and that column. 1, 2, 3, negative 1. So just a reminder how we find the determinant of a 3 by 3 matrix. This is I hat times, and we find the determinant of a 2 by 2 now. We do these two multiplied, 4, minus these two multiplied, 1. Minus j hat times these two, 2, minus these two, negative 3. It's really easy finding cross products to miss a negative sign, make an arithmetic error. So I recommend writing out in a little bit of detail so you don't make those errors. Plus k hat times these two, negative 1, minus 6. And when I add this all up, I get 3 I hat minus 5 j hat minus 7 k hat is u cross v. All right, so questions on the process there. All right, let's calculate v cross u. V cross u, we just change the order here, so we put v first, so it's going to be 3, negative 1, 2, 1, 2, negative 1 there. And the way I usually write this out when I do a cross product is I do I hat, and then I just mentally do the 2 by 2 determinant. So I cross that out and that out. So it's going to be 1 minus 4. And if it helps, you can do the plus minus plus up here. So remember that. Minus j hat. And then I'm going to cross that row and that column out. So my determinant is negative 3 minus 2 plus k hat times, I'm going to cross that row and that column out, 6 minus negative 1. And I usually write out my cross products like this, just so I don't make arithmetic errors. So I get negative 3 I hat plus 5 j hat plus 7 k hat. Now what do we see there? Here's u cross v and here's v cross u. The signs are switched, right? There's one and there's the other. Signs are switched. And we'll talk more about that in just a second. So all we did was change the order, but we got a different answer. The answer differed by a plus or a minus sign. All right, let's do, for the last one, let's do U cross U. So we're going to have I hat, J hat, K hat, and U is 1, 2, -1. So we get I hat times, cross out that column, that row, -2 minus -2. And if it helps, you can do your plus minus plus there. Minus J hat times -1 minus -1 plus K hat times, cross out that row, that column, 2 minus 2. And we get what? 2 plus 2, 1 plus 1, 2 minus 2, or -1 plus 1, 0 vector. And we'll talk more about that in just a second as well. And remember that the 0 vector does not equal the number 0. The 0 vector is different from the number 0. And it would be fine if you also wrote out, you could write 0 I hat plus 0 J hat plus 0 K hat. These two are the same thing. All right, questions there? Mm-hmm.
Why is everything if I have J hat, K hat are all 0,
Equals a 0 vector.
Right, what's the difference between 0 vector and point? 0, 0, 0.
One's a point and one's a vector.
Okay, so it's just different on how you manipulate it from there.
Right, right. All right. So let's talk about the properties. We saw with specific examples some of the properties of the cross product. Now we're going to list out a few more, just how we do arithmetic with cross products, and then we'll talk about the geometry. What is this telling us about what's going on with these vectors? All right. So our properties. Our first one we saw in our example is that U cross V equals negative V cross U. What this tells us is order matters. So we can't do the cross product just in any old order. We have to be careful with the order that we use when we do cross products. The fancy way of saying that is cross product is non-commutative. We can't just change the order. We can distribute using a cross product as long as we keep the order the same. So U cross V plus W, we can distribute just like we do with multiplication, but we have to keep the order the same. So this is U cross V plus U cross W. So we can't just change the order around. We have to keep it, this is being multiplied in the front, so we have to keep our cross product in the front to keep the order the right way. We can multiply a cross product by a scalar. And that's the same as multiplying either of the vectors by the scalar and then doing the cross product. But we have to keep the order the same. U has to come first every time. Mm-hmm.
Can you multiply the result of the cross product by a scalar?
Yeah, yeah. Yeah, that's what the first one is saying. If we take the cross product and multiply by the scalar, it's the same as multiplying either one by the Cross product of any vector with the 0 vector is the 0 vector. Mm-hmm.
For number 3, how can you not just distribute the whole vector for the scale?
It would be, it's kind of like saying, what we're saying here, we're thinking that this is multiplication. So this would be like 2 times 5 times 10. We don't say it's 2 times 5 times 2 times 10. We're just multiplying it once. So I think you're thinking of like we would do with addition. If it were addition, then we distribute it to both. The last one is any vector crossed with itself is the 0 vector. And this tells us something special about our vectors. If we cross 2 vectors and we get the 0 vector, and we'll talk about that in just a minute. And then we have this interesting product that comes up sometimes. U dot V cross W equals U cross V dot W. And we call this the scalar triple product. Or sometimes you'll hear it called the box product. We'll talk about why that is in just a minute. We won't do much with the scalar triple product, but it shows up every once in a while, and it's nice to know that it exists. All right, so questions on our arithmetic properties for the cross products. Okay, let's talk about what they tell us geometrically, because that's what makes them interesting. Geometry. My other class told me that there was lots of geometry on the ACT, and they didn't like it. All right, so our first one. This is an extremely important property of the cross product. U cross V is orthogonal to both U and V. And orthogonal, when we're talking about vectors, orthogonal means, what does that mean? 90 degrees. It makes a 90-degree angle with them. So the cross product makes a 90-degree angle with both U and V. So if we draw a picture of this, what this is showing us, that's a nice thing about geometry, is we can talk about pictures. So there's U and V. U cross V is orthogonal to both of them. And what that means is it makes a 90-degree angle with vector U, and it makes a 90-degree angle with vector V. And this is why we waited until we started talking about 3-dimensional vectors to find cross products, because we have to take the cross products, or when we take a cross product of 2 vectors, we get a vector that's not in the plane of the other 2 vectors anymore. So we have to talk about 3-dimensional vectors. So this is an important property that we use cross products for often. When we're talking about 3-dimensional surfaces, it's important to be able to find a vector that's orthogonal. Another word that we use for orthogonal is normal. A vector that's normal to the surface, makes a 90-degree angle with the surface. So that we use cross products for that, to find that normal, what we call a normal vector. Mm-hmm. Yeah, so since it changes the sign, if we can draw that in, that's a nice observation. This would be V cross U. So it just changes the direction. It makes it completely the opposite direction. And V cross U is still orthogonal to both U and V. So it just changes the direction. So that normal vector is important. So that reminds me. Do you know why the vector crossed the road to be normal? All right. Next property. The magnitude of U cross V equals the magnitude of U times the magnitude of V times sine of theta, and where theta is the angle between them. So let's draw a picture here. Here is so the magnitude of the cross product is the magnitude of the two vectors times the sine of the angle between them. So contrast that with the dot product. We said that U dot V is the magnitude of U times the magnitude of V times the cosine of the angle between the vectors. So the cross product gives us a relationship between the vectors and the sine of the angle between them. Dot product gives us a relationship between the vectors and the cosine of the angle between them. This next one is a nice property that gets used a lot. U cross V is the zero vector if and only if U and V are parallel. So if the cross product of two vectors is 0, that tells us immediately that those two vectors are parallel. And if we know that the vectors are parallel, we know without even doing the cross product that the cross product is going to be 0. And we can see that here if the two vectors are parallel, the angle between them is 0, and the sine of 0 is 0. So the magnitude of U cross V is going to be 0. We get a lot of good information from the cross product. And the last one, another very, very important property of the cross product. The magnitude of U cross V equals the area of the parallelogram. With U and V as adjacent sides. So if we draw a picture here, if that's U and V, if we turn that into a little parallelogram, like so, there's my parallelogram with U and V as adjacent sides. The area here equals the magnitude of U cross V. This is another extremely important use of cross products. We use a cross product to find areas. So if we have some kind of surface in 3 dimensions, and we can form two vectors on the surface, and we can take a cross product of those two vectors. That gives us the area of a little piece of the surface. We can add those up, and we get the surface area of this crazy 3-dimensional surface. We use that cross product as an area extensively. Yes.
So does this still work with the at 90 degrees to each other?
Mm-hmm. So then the parallelogram would be a rectangle.
Yeah.
And then just so you know, we're not going to do very much with it, but we did that the scalar triple product. So I'm going to say u dot v cross w, and I'm going to say the absolute value of this because we want it to be positive, equals the volume of the box. Fancy word for box is parallelepiped, because we would make another side that comes up, so it's kind of a little slanted box. Volume of the box with u, v, and w as adjacent sides. So that scalar triple product gives us the volume of a little box. So if I drew a vector up here and turned this into kind of a box shape, that scalar triple product would give us the volume of that box. That's why it's called the box. It's sometimes called the box product. Won't do a lot with it, but it's a nice little thing to know. All right, questions there? So all of these, the geometric properties of cross product, that's where it ends up. We end up using cross products mostly because of their geometric properties, not just to do them, but because these things are true about cross products, and they turn out to be extremely useful when you're talking about three-dimensional geometry. Cross products turn up a lot in electricity, magnetism, gravitation. When you talk about fluid mechanics, fluids flowing around, you use these ideas of cross products just like all the time. All right, so I just want to do a couple of examples that have to do with these geometric ideas, and then we'll be done. All right. So the first one, we want the question asks us find a unit vector to both u equals I hat minus 2 j hat minus 3 k hat, and v equals 4 j hat minus 5 k hat. So first off, let's translate what this question is asking us to do. Unit vector orthogonal to both of these vectors. So this part that says orthogonal to both, what is that telling us to do? How do we find a vector that's orthogonal to both vectors, two vectors that we already know? Cross product. So this is saying find, we're kind of translating what this is asking. Find u cross v. That will give us our vector that's orthogonal to both. And then it wants a unit vector. So once we have a vector, how do we turn it into a unit vector? Divide by the magnitude. Find u cross v, and then divide by the magnitude. Anytime you see unit vector, you're talking about vectors and you see unit vector, you should think, okay, I have to divide by the magnitude. So what this question is really asking us is find u cross v, and then divide by the magnitude. All right, so here's what I want to do. U cross v, I want you guys to find u cross v and tell me what it is. We'll write out the determinant here. I have 1, -2, -3. Since this has no I hat component, what goes here? 0. I have to put a placeholder. 4 and -5. All right, so you guys calculate that cross product and tell me what it is. Be careful with your pluses and minuses. That's the most common mistake with cross products. You miss a plus or a minus somewhere. All right, did we get it? What's our I hat component? 22. 22 I hat. J hat component. What is it? Negative 5? Positive 5. Remember I think you might have forgotten your plus, minus, plus. So that should be plus 5 j hat, and then the k component, k hat, plus 4. So there's our vector orthogonal to both u and v. What if the question, before we find the unit vector, what if the question said, show that this vector is orthogonal to u and v? What would we do? How could we show that this vector is orthogonal to both u and v? What tells us when two vectors are orthogonal? What is it? The dot product is 0. So if we did the dot product of this with this, we should get 0. And if we did the dot product of this with this, we should get 0. That's how we show the two vectors are orthogonal. Take the dot product, it should equal 0. All right, so we want to divide this vector by the magnitude. So the magnitude of u cross v. So you guys calculate that magnitude. Tell me what that is. I will divide the vector by the magnitude. I'll get us started. Square root. What does it come out to? 521? I think we made arithmetic here. Anybody else get it? 22 squared plus 5 squared plus 4 squared? $525. 22 square root of 22 squared plus 5 squared plus 4 squared. And does it simplify? To 525 is square root of 25 times 21. So this is going to be 5 square root 21. Oh, that's where the 21 came from? Yeah. Okay. All right, so then our unit vector, we're going to divide this vector by its magnitude. So we get 22 over 5 square root 21 I hat plus, here when I divide by 5 square root 21, I just get a 1 over square root 21 j hat plus 4 over 5 square root 21 k hat. And I could also write this, I could have just written 1 over 5 square root 21. It's the same as dividing by the magnitude times this whole thing. 22 I hat plus 5 j hat plus 4 k hat. These two are the same thing. And either one is fine. And I wouldn't make you rationalize that. All right, questions there? Yes.
If you put 22 like I hat plus 5 to over 5, so it's really
Oh, so just kind of write it like this, and then just put that in the dom. Yeah, that would be fine. Yeah. So three different ways you could write it. And you could also write this in component form with the angle bracket and not with the I hat, J hat, K hat. Doesn't really matter. They're all the same. They're all the same notation. I mean, same. They tell the same thing with different notation. All right, last example. Find the area. We want to find the area of the parallelogram with vertices at point P, which is 1, 1, 1. Q, which is 2, 3, negative 1. R, which is points negative 1, negative 2, 2. And S, which is at point 0, 0, 0. All right, so what is this problem asking us to do? We have the area we want the area of the parallelogram. It'd be really hard to do if we tried to draw a picture or something like that. Magnitude of the cross product, right? Of the cross product, and we need to form the cross product with what? We need two vectors that make up adjacent sides. So we have to figure out which sides are adjacent, because if we're not careful, we could be forming the cross product if we make our parallelogram. If we choose our sides the wrong way, choose our vectors the wrong way, we could be using the vector that makes up the diagonal instead of the vector that makes up adjacent sides. So we need to figure out which. If we're going to make vectors, which pair of vectors make up adjacent sides of this parallelogram, to avoid using the diagonal as one of our vectors. So how do we do that? How do we decide which pairs of these make up adjacent sides? Okay, so there's one thing that we could do. We could use the distance formula and find which pairs, because the opposite sides of a parallelogram are congruent, so which pairs are the same lengths, and then a pair of adjacent sides has to be the two that are two different lengths, unless it's a square and then they'd be the same, or a rhombus and then they'd all be the same. So that's one way we could do it. That would take some calculation, some computation, but it's doable. Another way, similar to that geometric idea. What do we know about the opposite? What else do we know about the opposite sides of parallelograms? They're parallel. That's in the name, right? So we could form vectors and see which pairs are parallel. Same kind of idea. Which pairs are parallel. So that's another way we could do it. Just kind of thinking geometrically. Is there another way we could do it? The third way is the way I did it. I drew a picture to decide which ones were parallel. So I just made a little sketch and plotted points. We have one point at 0, 0, 0. That's point S. We have one point at 1, 1, 1, so we're going over 1, and up 1. So roughly, I'm just going to plot point P up here. So I'm going over 1, and up 1. So there's point P. Point R is at -1, -2, and +2. So point R would be roughly here. And I'm going back here and over here and up. And then, where's the next one? 2, 3, -1. So I'm going to 2, 3, and -1. There's point P. So here's my parallelogram. So that's how I did it, just to visualize the sides. So either of those three ways would work. And then I used, wait, which one did I mislabel? This one is 2, 3, this is point Q. Over 2, 3, and then down 1. This is point Q. So I use the vectors. You could choose any pair that make up adjacent sides. I did the magnitude of PQ cross PR. So I did this vector and this vector as adjacent sides. So we found the magnitude of PQ and PR. So I'm not going to go through, we don't necessarily need to go through the calculations of finding the magnitude of the cross product. We've done a bunch of cross products. But let's make sure we remember, how do we find PQ? How do we find the vector between those 2 points? What's our shorthand way of thinking about it? How did you do your problem, Nikki? Terminal minus initial, right? So PQ would be the vector, we're saying Q is a terminal point, would be the vector 1, 2 minus 1, 3 minus 1 is 2, and -1 minus 1 is -2. And then PR, same thing, terminal minus initial. PR, when I do that, I get -2, -3, 1. So we would find the magnitude of PQ cross PR. So I'm just going to write this out. We'll not do the calculations. 1, 2, -2, -2, -3, 1. So there's our cross product. We would find the magnitude of that, and we come up with when I did this problem, I came up with the area equals the square root of 26. Now what if this problem said find the area, and then also asked, is this parallelogram a rectangle? How would we answer that question? One way that Roland came up with, what was your idea?
So what I was going to say is, if all sides if they're orthogonal, just calculate the orthogonal sides.
Calculate, and how do we calculate the orthogonal sides? What do we do? Well, that gives us an orthogonal vector. The dot product would equal 0. The dot product between two adjacent sides would be 0. So we would find two adjacent sides and see if the dot product was 0. So when we calculate the dot product equals 0, that tells us if vectors are orthogonal. So that would be one way we could test if this parallelogram was a rectangle. And then back to the geometry idea, what's another way we could decide if it was a rectangle? Well, we'd have to know the angles were 90 degrees, right? But if we wanted to know if it was a square, then we could calculate the lengths of the sides. So the test for orthogonal vectors is the dot product equals 0. To produce an orthogonal vector, we do the cross product. All right, questions? Okay. All right, there we go.